For joining DataCon LA 2021, and welcome to the Emerging Tech Track. My name is Joanna Perdomo, one of your hosts, and our co-host today is Delapo Kester. We'll be moderating the chat and the Q&A for you during the session. We have our guest today, Shae Wang, and she's going to be talking about evaluating blockchains through the lens of data. Shae is a staff data scientist at Ripple. She leads Ripple's efforts around blockchain data and developer experience. Before joining the blockchain industry, Shae was a data scientist at Uber for a few years and worked on a wide range of problems from OCR modeling and churn modeling to causal inference. Prior to her role at Uber, Shae used neural nets to predict stock market movements for a startup and also ran her own self-storage startup on her college campus. She earned her master's in computer science with a focus in machine learning and a bachelor's degree in statistics from Northwestern University. And without further ado, I'll hand it over to our speaker. Thanks for being here, Shae.
Thanks for the introduction, Joanna, and thank you for having me here. So hello, everyone. My name is Shae Wang, and I work in data science at Ripple, which is a blockchain technology fintech company. I have to say thank you to the organizers of DataCon LA for inviting me here today. I run data science on a team called Ripple X. It's where the open source public XRP ledger, which is the blockchain protocol, and Ripple's cross-border payment product kind of intersect. And what really drives our initiatives behind contributing to core features and building new use cases in crypto, like things like NFTs. If any of these don't really make sense yet, hopefully they will after this talk. I was actually really excited to see that blockchain was listed as a topic in the emerging tech track for this conference. The rise in innovation and adoption of blockchain, cryptographic, and decentralized ledgers is a definitive trait of this decade's technology for sure. Nowadays, we can't really go by a single day without hearing about an insane spike in a cryptocurrency's price or a new NFT series selling for millions of dollars or yield farming. There's so much speculation and also excitement around the future of various blockchain projects. As one of the few data scientists working in core blockchain protocols, I often get questions about what I actually do and what cryptocurrencies people should buy. Well, I can't give investment advice, nor can I predict prices. I'm here to give you an overview of the data science space in blockchain and how methods and frameworks we're pretty familiar with in data science could be applied to solve analytics and scientific problems in blockchain. For the rest of this talk, I will actually be referring to this family of technologies from blockchain to the use of cryptographic keys as just blockchain in general, as they're often used together for blockchain protocols. But just know that they are separate and the technology kind of takes advantage of different pieces of these various technologies. So, but the distinction becomes critical if we really get into deeper discussions around blockchain applications, but it's not really necessary for our purpose today. To kick things off, we need to understand why blockchain technology exists, what problems builders in this space are actually trying to solve, and what the technology roughly looks like. This is to ensure that we are all aligned at the same level of understanding about the foundational technology. It's a pretty common misconception that blockchain is a solution to a problem we have yet to define. It's a solution looking for a problem, but blockchain was actually invented to solve a real problem that has always been hidden from everyday consumers like you and me. It set out to solve how we transfer a digital asset between two peers without any intermediary. There are many applications of this transfer. We've all heard of artwork NFTs, for example, but let's just look at it in the context of money. Let's say that you are an online bookseller and some user named Alice buys a book from you. You don't know anything about this Alice person, and you have no idea if they have the money they say they do to pay you for the book. Therefore, maybe you trust the middleman to verify what you cannot and help you manage the risks involved with such a transaction. For example, you may use PayPal to accept the payment from Alice. PayPal then works with Alice's bank to make sure that Alice is good for their word and transfers the funds from Alice's account to your account. PayPal and the banks in this situation are the intermediaries that facilitate your transaction, and for their labor and communication, you must pay a fee and the cost of potential time delay. The asymmetry of trust in this transaction is actually a well-studied decentralized computer systems problem known as the Byzantine generals problem. Imagine we have a couple of generals planning to attack a city. At least some number, let's say 3 out of 4 of the generals, must attack at the same time to overpower the army holding the city. However, the only way they can communicate with each other is via a messenger, and they do not know if one of the generals is a traitor. If there is a traitor, he must modify the attack message and cause the other generals to fail. And the only way to solve this problem is to have everyone review the full history of messages sent and received between all of the different generals. And if the majority of generals are good, then they could easily identify the traitors and ignore these altered messages. I want you to imagine that these generals are computers in a network trying to validate payment transactions, for example. Certain generals could actually be altering past transaction histories in order to gain profit. In the book-selling example, we cannot see Alice's full transaction history. Therefore, PayPal and the banks act as a clearinghouse system. The reason for wanting to improve this mode of operation is just simply efficiency, cost, privacy, accessibility, and actually security. So how does blockchain solve this problem from an architecture perspective? Simply put, instead of having a central clearinghouse, for example, a central bank, determine the order and results of transactions, a majority of the users on the platform agree to validate the authenticity of the transactions. So everybody votes. It's a very democratic system. And by users, I'm actually referring to nodes. And these nodes in the early days could be a simple computer with a CPU, but nowadays, sometimes we need specialized machines just because of how much these blockchains have actually scaled. Let's say that Alice claims to send you the funds for their purchase. First, this transaction is grouped together with other transactions in blocks. Then nodes or computers use an algorithmic method to validate the transactions and add the block to previous blocks. And together, these blocks form a chain. Because all future blocks are connected to and dependent on previous blocks, it is pretty much impossible to alter or delete previous transactions. Since once you delete a previous transaction, future blocks are actually invalidated because they're all algorithmically connected together. This is why blockchain is considered to be immutable. As long as the transaction data is not corrupt, everybody on the network could actually see what's going on, and we could trust the full history without any third party and interact in a trustless exchange of digital assets. Every major blockchain technology has a slightly different implementation of these algorithms that decide if how blocks should be added. You may have heard of the proof of work algorithm that is used by the Bitcoin network and the Ethereum network. There's also proof of stake algorithm used by Ethereum 2.0, the proof of history algorithm used by Solana, and the federated consensus algorithm used by the XRP ledger. Now that we understand the motivation and basic makeup of a blockchain, let's dive into the fun topics of how we could apply data science methodologies to solve various problems a blockchain or blockchain-based business could face. I know that our audience today is made up of data professionals from all disciplines, so I'll try to make this relevant and interesting to all of you by deep diving into 3 main problems across engineering and modeling. The first problem we will dig into is this. How do we evaluate different blockchains? By evaluation, I don't mean speculating how the price of the underlying tokens for the blockchain will change over time, but rather, how do we capture the fundamentals and growth of a blockchain technology? Because there are typically tokens that are tradable associated with the blockchain, the ones you see on Coinbase or Binance. Its value actually comes from 2 places. Number 1 is speculation of the market. Number 2 is the utility of the chain itself. Just because a token price has increased, that may not translate into more adoption and utility of the chain itself. And here I must differentiate that when we talk about utility of the chain itself, we're talking about transactions that are happening on chain. The definition is exactly kind of the workflow that we just saw when a transaction is added to a block and the block gets validated. So all that stuff, that's on chain. Now, when you trade on Coinbase, sometimes that transaction is just happening in the backend in Coinbase's database. No on-chain transaction actually happened. And a lot of speculation on the market and the crypto market kind of happens that way. So the market for trading is actually extremely volatile. Anyone that's invested in the crypto market could probably attest to that, and often based on a lot of hype and not fundamentals. From the data science perspective, having a framework and the right metrics designed to measure the effectiveness and growth of a blockchain technology, aside from all the noises, will help us understand how they're performing from an empirical angle. And this is really valuable information for any team of builders as they make future changes to the protocol itself. Let's break down the high-level questions about on-chain utility and growth into more concrete questions. We've visited the motivation behind blockchain technology before, which is to enable trustless transfer of value in a peer-to-peer fashion. Therefore, if there's more value being transferred on the blockchain, there's more actual utility of the core technology. We need to know how much value is being transferred. And the second thing is we need to know how many total transfers have happened. And 3, how many peers are in this peer-to-peer network? Is there a way to crawl through an entire blockchain and get the data we need to answer these questions? The answer is yes. To measure how much value is being transferred, we use the metric total transfer volume. Total transfer volume is defined as the total amount of coins or tokens transferred on-chain successfully, aggregated from all the transactions. Here's an example of what the metric looks like. This chart is the total transfer volume of XRP over time. When we use the total transfer volume metric, it's important to look at the volume in units of the native token, as well as another more stable currency, US dollars, for example. And this is because there's so much market volatility in the price of any token, and the total amount of tokens transferred may be impacted. You may ask, well, both this token and US dollars function like currencies. Why is one so much more volatile than the other? This is because for US dollars, there's a central agency regulating its price, and that's the government. To ensure that you aren't paying $1 for something today and $20 tomorrow, the Federal Reserve changes the Fed fund rates, total supply of money, and works with other government agencies on various fiscal policies to stabilize the price of USD. This kind of regulation does not exist in cryptocurrencies today, unless their values are pegged against a regulated currency. We may also want to look at how many total transfers happened using the metric number of transactions. This metric is very straightforward. Number of transactions is just the total amount of transactions. Here is an example of what the metric looks like for XRP. The number of transactions is determined by the demand for transactions, of course, but it's also constrained by how many transactions could actually be executed by the blockchain in any given time period. This is why when we compare the number of transactions between different blockchains, we also include typically the transaction rate and the transaction speed metric to give more context around the constraint. There's actually a very high variance in transaction speed and throughput for different cryptocurrencies, and even for the same cryptocurrency at different times. For example, an XRP transaction takes about 3 seconds to be validated by the chain, but an Ethereum transaction could actually take anywhere from 15 seconds to a day to confirm, depending on the network's own latency and how much you're willing to pay to prioritize the transaction. To measure how many peers are in this peer-to-peer network, we will use the metric number of addresses. An address is sort of similar to the idea of a user ID. By measuring how many addresses are on the ledger, we could estimate how many participants are on the chain. We may also want to evaluate the growth rate of the number of addresses by looking at new addresses created every day. We also want to look at how many active addresses are there sometimes and the retention rate of these addresses to understand the engagement and activity of these participants on the network. The more active addresses, the better. When interpreting metrics around addresses, it's important to remember that the blockchain is anonymous, so you don't have any metadata about the participant. It's very not similar to, for example, the data you would see from a B2C company. For all we know, the address may not even be a real person or is just one of many bots that belong to someone. Depending on the cost of creating a new address, which is often zero for many chains, one person may have multiple addresses created at various times, some active while others have been forgotten about. These metrics are foundational to on-chain analytics, but just the tip of the iceberg of what we can measure on the blockchain. The way we obtain these metrics is often by crawling through the blockchain and writing ETLs to aggregate this information. Some blockchains are well studied, and we could find great open source data tables to do our calculations. Other ones still exist in their raw blockchain format, and it takes a huge amount of work to parse the data. Nowadays, many blockchains store their data on Graph, which is an indexing protocol for querying blockchain data, and it's decentralized. And also, luckily, there has been a significant growth on-chain analytics over the past year, and there are many analytics startups emerging to attempt to surface the data and metrics across many different blockchains via data APIs. Now that we have the fundamental measurements, I want to take it up a notch and discuss the second problem, which is how do we measure real peer-to-peer utility of the blockchain? I just mentioned that there could be some addresses on there that are bots. So there's some important context around this problem. The first one is that there are many different types of underlying entities on the blockchain. I could have an address that represents me. An online store could have an address that represents their account. A payment service provider could have another address. And a payment service provider may actually sound like it's defeating the purpose of blockchain, but it's actually still required today just because of how hard it is to make different blockchains interoperate and talk to each other. An exchange like Coinbase could have an address on the ledger. Actually, they would have multiple addresses. It's important to have diversity of various entities because that shows the breadth of what transactions are used for. But we also want there to be a good balance of peer-to-peer and peer to a centralized entity or a payment provider or exchange transactions. The second piece of context here that makes this problem really interesting is the fact that there are a lot of transaction patterns on the blockchain. Most transactions seem to be from A to B. Sometimes, either to add an extra layer of security or for other reasons, A would not directly send to B, but send to another address C first, only for C to forward to B within seconds. This chain of transactions could grow indefinitely long and include cycles, but really just represents one transaction. While we measure the total volume of transactions and like the fact that people have the freedom to use the blockchain however they want, we are curious about the real value of a series of transactions so we could lower the amount of noise we see in growth-related analyses. The first issue, which is, does any given address represent a peer or a centralized entity, is actually a classic classification problem. I have tried my hands at this problem myself, and it's not unusual for centralized entities like exchanges and payment providers to publish some of their addresses so that they could participate in different analytics platforms. Or if you're a user depositing funds into the service, you could double check that the addresses you're using are the right ones. Although that's not a recommended method, you may find these types of annotated lists on the internet. But the classification problem is not nearly solved because the list of annotated addresses is usually a tiny fraction of all the central entity addresses on the ledger. There are many hidden addresses those central entities use to add security for their blockchain addresses. Imagine if a bank published all of their cash vault addresses that would be asking to get robbed. One potential solution is to reweight our imbalanced data set and use a classification model like logistic regression, support vector machines, or XGBoost. As part of the data set, we consider features about the addresses themselves, such as when they were created, how much they were funded with. We should also include behavior patterns of these addresses, such as how often they send and receive transactions, how big are their transaction sizes, when do they typically send and receive transactions, what is their address balance, how volatile is their address balance, how big is the network that they transact with, etc. Having calculated all of these features, we could then upweight the central entity class in our small batch of dataset and apply a classification algorithm to select the most important features and output some predictions on the probability of these addresses being either type. One issue I've personally encountered is that it's incredibly difficult to obtain the small batch of dataset for training purposes because there's often no way to even manually label it, as you have no way of verifying if the labeling is correct. Another issue is that there is so much variance in how central entities all behave. It's often important that we derive features that effectively capture distinct qualities between central entities and peers rather than among central entities themselves. For example, we may want to encode address balances as levels because maybe a central entity could have anything between 100 to 100 million, but the magnitude of that difference isn't really meaningful for our model. Another potential solution is using a semi-supervised learning algorithm. If you're unfamiliar with semi-supervised learning, it's an approach that combines a small amount of labeled data with a large amount of unlabeled data during training. We could just use unsupervised learning on the data and maybe clustering to detect some underlying patterns. But unlabeled data, when used in conjunction with just a small amount of labeled data, could actually produce considerable improvement in learning accuracy. And maybe addresses can be represented as points in a hyperspace defined by all of their features. Points that are closer to each other are more similar. We'll keep this at a high level to avoid really dense technical details. But I highly encourage you to think about this problem on your own. It's actually been somewhat studied in the blockchain space, but current methodologies could always use creative improvements. Now let's talk about the second issue, which requires us to detect cycles and forwarded transactions. This pattern of transactions is typically referred to as churn in the blockchain analytics space. Of course, we could apply heuristics. Let's define, say, a boundary of time, maybe 1 second, and then look at transactions from A. Did a similar amount go through B and C to eventually reach D? Or are B and C typically only involved in transactions between A and D? This approach may seem intuitive, and I do believe starting here is the right approach to just getting some basic numbers on the table. But you probably already realize that this approach has limited flexibility and loses its effectiveness quickly as we scale these transaction chains. What if instead of sending the same amount to B, A divided the amount to distribute across many addresses before aggregating them towards D? The computational power needed for these heuristics often grows exponentially as the blockchain's peer network and transactions grow. The data science problems in blockchain like the ones that I just mentioned, are not entirely new to traditional data scientists. Many of us that have tried modeling in a real-world environment have probably come across the data labeling issue and could tell you that real-world data sets are very, very different from what's on Kaggle. Sometimes the cost of data labeling is really high. We don't have the full training data set and need to get creative about how we use our limited batch of labeled data. The one in blockchain is interesting because it's such an extreme case of small labeled data. Out of millions of addresses on the ledger, sometimes only about 300 or 400 are self-reported by central entities. The last problem we will discuss today is for those of you that spend a lot of time thinking about data storage architecture and schema design, and that is, how should we store blockchain data to answer these different analytics questions very efficiently and effectively? How should we store them to scale? Remember that the raw data of any blockchain exists on the blockchain itself. Transactions are packaged to be validated in blocks. There is some data engineering magic to parse the data efficiently. But after that, to enable effective downstream analytics, what kind of tables do we need? I think the most straightforward and useful structure for aggregation like analytics and even some machine learning models would be a relational database structured maybe as such. We have transaction tables of all of the transactions and their metadata. We have blocks or ledger tables with all the blocks and which transactions were processed on each block, and address tables of all of the addresses and their metadata. The Snowflake schema using fact and dimensional tables apply really well here. There may be other tables that capture idiosyncratic features, but these tables are the ones that are shared between almost all blockchains. From these tables, it becomes very easy to create model tables of metrics and how they change over time. What's really amazing about blockchain data is that it's unlikely to be corrupted or wrong unless it's a downstream issue. On my team, I would work with data engineers to define a requirement for such a database, and we would build out the infrastructure to support parsing the raw data. But what if we wanted to detect churn transactions? Is the schema still useful for that? If you remember, churn transactions are a series of transactions that hops through addresses. They may also contain cycles or be broken up into various amounts across addresses. Because the transaction table is just a flat table, if we used our Snowflake schema, it would actually be very, very difficult to detect these hidden structures. In my opinion, a better storage solution for this problem would be using a graph database structure like NoSQL. The graph model will be able to explicitly lay out the dependencies between nodes in our network and help us enforce checks much more efficiently as we traverse through the network. It's also possible to use flat tables, but we would need the extra step of converting our flat table into a giant directed graph. The biggest challenge with using a graph-native data structure solution is that there really isn't a university graph query language today that's widely adopted and easy to use. We cannot just write something similar to a SQL query to pull what we want from the graph and define these relationships. Therefore, implementing these data cleaning tasks would actually require a non-insignificant amount of engineering effort. There are a ton of improvements that could be made to both the storage design and general accessibility of blockchain data. Even though all the data is public on the blockchain, many blockchains do not have open source tables that are ready to be analyzed. As data analysts and scientists, we often need to rely on native integrations with the blockchains themselves and build the entire data pipeline from scratch. Some blockchain analytics startups offer data APIs, but they also have to go through the same hurdles and deal with a lot of nuances between how different blockchains are implemented and their various native architectures. This leads to a huge lag in when blockchain technology ramp up on the product side and adoption side, and when their data actually becomes available to the public eye and for data scientists to do their analyses. There are some other really interesting and nascent problems data science could help solve in blockchain. One I must mention is in the decentralized finance space around optimally designing pricing formulas and liquidity incentives for peer-to-peer lending and automated market making. These are peer-to-peer lending or exchange solutions that rely on a complex mix of design decisions between engineering, econometrics, and mathematics. The other one I must also mention is the use of artificial intelligence in Web 3.0. Web 3.0 is a new concept about how the internet should be structured. It envisions that data will be interconnected in a decentralized way, which would be a huge leap forward to our current generation of the internet, which is Web 2.0. Web 2.0 is where the data is mostly stored in centralized repositories, and they can be sold for a price, for example. In the current internet, big brothers get to really take profits on user data and build mind-changing algorithms. So Web 3.0 imagines that you custody your own data. Part of making this vision possible is an incredible amount of artificial intelligence and natural language processing so that computers can understand information like humans in order to provide faster and more relevant results. As with any nascent technology, data science and analytics are often overlooked in the beginning in favor of developing features and shipping new releases. But as technologies become more mature and get more adoption, data science becomes increasingly more valuable and useful, necessary for every one of these blockchain projects. The blockchain space is built by open source communities of software developers, and that's why there's such fast and incredible innovation. But there isn't really an open source community of data scientists and engineers. So I hope now that you can be as excited as I am about data science in the blockchain space and inspired to try your hands at some of these problems yourself. I am active on Twitter, LinkedIn, and of course, Discord and Telegram. So feel free to reach me via any of these channels to chat. And now I think we have an extra 15 minutes, so I'll open up the floor for Q&A if we have any in the chat.
Wow, that was very impressive, Shae, and thank you so much for sharing such a complicated subject or topic. I know we hear about blockchain, crypto, but how you made it simple and letting us be aware of how blockchain or how the mechanisms of it affects how simple infrastructure that we have already in place, comparisons. For you talked about the banks and how transaction goes from one place to the other. Was wondering if anyone has questions. If you can please put it on the session tab, question and answer, to see if anyone would have questions for Shae. But while someone is trying to ask those questions, I have one question for you. Since blockchain started, I'm not sure how long it's been, or the idea of crypto or blockchain itself. I heard of it a while ago, about 6 years ago. It was nascent. Think people didn't understand. I didn't understand it either. Um, the idea was there are. You mentioned something about peer to peer, so computers talking to computers, and we talked about network. What I was interested in knowing, understanding is the latency. When I do something, how quick or how there's a lot of people. I don't know what type of, it's a special network or if it's any type of network that AT&T provides me on my cell phone, or and how is this only for a group of people that are only blockchain people, or is this for the whole public?
Yeah, thank you for the questions. So I think I can break that up into two parts. The first question about latency. So that's a really, really interesting question, because today, as we experience transfers, for example, peer-to-peer, first thing we think of is Venmo. When you Venmo somebody, it instantly appears in their account. That's actually an illusion. It doesn't actually appear in their account. The bank actually, settles it. I think it really depends on, how Venmo is dealing with this under the hood. But typically, bank settles transactions, within like 1 to 3 days. That's actually how fast it takes for transactions to take place. There's a certain amount of risks, obviously, associated with that, that a lot of times are obfuscated from the users themselves. And that's also why sometimes in a bank situation, you can reverse transactions. And, on a user side, you may kind of like that experience. Maybe I can, turn a transaction back around. But sometimes for merchants, it's actually a really bad experience to be able for users to reverse transactions, because sometimes it is actually a false alarm, and kind of these false negatives kind of do happen in the space. So having benchmarked latency in the real world, what does latency on blockchain looks like? On XRP, it takes about 3 seconds on average for a transaction to be fully validated. And that means that it's done. That just is it's like the bank debiting and crediting. All of that has already happened within 3 seconds. That is kind of, I think, the new standards that all of the different chains are trying to move towards. You would see any range between 3 seconds right now to say 10 to 20 seconds of transactions being validated. The second question, about like accessibility. It is really open to anyone. You are free to kind of create your own cryptocurrency account with any kind of blockchain. And there is really no kind of checks and process involved with it. And this is kind of the challenge with the blockchain space, is that there isn't much clearer guidelines around regulation. And because there isn't that, but then for a bank, you kind of have to go through like KYC, AML. If there's anyone working in fintech here, you're probably familiar with those terms. You have to upload your like passport, maybe, I don't know, ID. There isn't those checks that's really consistently enforced across different blockchains. It's actually even a little more open, where, today it might be hard for Dolapo you to send a payment all the way to, say, I don't know, China, but then on blockchain, there's no concept of country borders. So you can do that pretty effectively.
Oh, great. Thank you so much. I think there's some questions in the chat. If you don't mind me asking, question says here, how comfortable were you with blockchain, its underlying concepts, and XRP when you first applied for the role?
When I first applied for the role 2 years ago, I had no idea how any of this worked. Zero foundation, and I was pretty transparent with the company when I was interviewing. I was like, hey, I actually don't know anything, but it's actually okay, and they're kind of looking for people that come from very different disciplines to bring in their knowledge to be able to solve these problems, because I do think it adds a lot of different perspectives. Blockchain so far, as I've kind of said in the talk, it's very, very developer and engineering driven. And because of that, sometimes they ignore a lot of problems. You would see a lot of blockchains, they've already launched the product for maybe like 2 years, and they have no measurement of, for example, growth metrics. They have no marketing tactics, and they have none of this. They just have this core technology sitting there. And so it's actually really, really, it's a great time to bring in folks from other industries or disciplines to bring in their new perspectives on what problems they could be having.
Yeah, great. Thank you so much for answering that. Another question here, I see, what other projects are you interested in this space, if any?
What other projects am I really interested in? I think that I'm excited to see where NFTs go. Number one, I think that NFTs are definitely overhyped right now. I'm not saying that. I'm not saying everybody should go out and buy JPEGs, digital art, for a crazy amount of money. But I do think that there's a lot of extension of those use cases that could be really, really interesting. They could be experiential or functional NFTs applied to, say, tokenizing financial assets, real estate assets. It could be used for, just kind of denoting a lot of like physical assets, physical art. And so I'm looking forward to see what kind of innovations happen there. And the second thing is definitely decentralized finance. I think that there's a lot of cool innovations in this space. If you have the time, definitely take some time to read and learn about automated market making. It's such an interesting concept and a great way to gain some insight into kind of how decentralized finance works today.
Oh, thank you for bringing that decentralized finance. One thing is, instead of actually it manually having people go through different stages of processes, you can just have computers have those configurations or ledgers on a peer-to-peer level and then talk to each other, instead of going through different individual breakdowns of every single process individually manually. But decentralized is two of the having a general rule for both parties, like you talked about peer-to-peer and be able to exchange seamlessly. So thank you for that. Another question here is, did you consider Neo 4J as your graph database? And how did you end up choosing the one you mentioned in your talk?
Thank you for the question. So I actually usually rely on my amazing team of data engineers to tell me what is the right database based on whatever requirements I have. Usually, so I work on the data science side, and I pretty much just go to them with my, maybe it's like latency requirements and the business context and the actual problem. And I rely on them to build out the engineering spec from the data engineering perspective. So did I consider Neo4j? I personally did not, but I know that it was like one of the graph database that we were evaluating among other ones. We actually don't use currently graph database to store any of this data right now. It has not been implemented at all. But I do know that there is a something called the Graph. If you look it up, it is an open source, decentralized graph database to store blockchain data. And now a lot of blockchains are actually moving, or not moving, but they're actually storing their data or a copy of their data there. And that's because of kind of the decentralized and open source nature of a lot of these blockchain projects. They don't want to kind of limit it to any single person or any single entity, institution to access. So a lot of times the prioritization when it comes down to choosing databases, how easy is it to make it decentralized and distributed. And so I think the graph definitely emerged as one of the preferred solutions today over some of these other graph databases that work better for enterprises.
Okay, great. I think I do have one last question. I was thinking most of the data that you analyze in the exchange, are those based on proprietary? I mean, are they sole owned data or data from other places that other banks that are exposed to you that you kind of use for business case or anything?
So for exchange data that you mentioned, usually cryptocurrency exchanges and usually generally exchanges all around, they kind of provide access to their data, and what that data would be might be like ticks and order book. And they actually use APIs to expose most of this data to businesses, just because a lot of times exchanges actually rely on these kind of automated, like either it's like user interface or automated trading platforms to bring them a lot of volume. And they also integrate with usually like market makers, for example, to facilitate their trade. So we expect like kind of having, access to the same kind of data, say from Binance or Coinbase. In terms of like those entities and their addresses, so usually there is a certain business called block explorers. Block explorers, you can find them for one or at least one for almost every single blockchain. They kind of expose a lot of this metric and information about what's actually happening on the blockchain. And oftentimes like a business or an entity might go to them and say, hey, you can tell everybody that this address belongs to me. And that is publicly available.
Great. Well, thank you so much, Shae. This is very informative, very insightful topic, and thank you for giving us as much breadth of knowledge of blockchain and data science around it. We have a couple of minutes left. I was wondering if anyone else has any questions. Just a couple, 3 minutes to add. Thank you. And I would like to also thank all the attendees and also your questions that you've asked. I have a couple of minutes for any more questions. Thank you.
All right. Well, thank you, Delapo, and thanks to everyone for joining.
Well, thank you, Shae, and thank you everyone for attending, all the attendees. It's a great pleasure to have you, and thank you for being a part of DataCon 2021. We hope to, and any one of the attendees, if you want to reach out to Shae in the future, or if you have more questions, I think she mentioned she gave some of her information, and we also have some of the information on the calendar, and we'll also be providing more of those after the whole session or the session today ends. Thank you so much.
Awesome. Have a great weekend.
Have a good weekend. Take care.